second presentation is Numerical Methods for Propeller Cavitation and Noise by Mr. J. Ramkumar, Senior Surveyor at IR class. Just a minute. Over to you, sir.
So hello, good evening everyone. I'm Ram Kumar from Indian Register of Shipping. So today I'm going to talk about numerical methods that are available for modeling propeller cavitation, and I'll give a brief introduction about noise, both near field and far field noise estimation. So the topics that I'll be covering are introduction to noise, and what are the various sources of noise in the context of vessel. Okay. In the context of vessel operation. And then I'll be talking about propeller noise sources and what is the importance of numerical estimation of propeller noise in the design phase and how cavitation plays a role in that. And then I'll be covering mostly about types of cavitation in propeller. And then we will be talking about a validation study that we have performed to numerically estimate propeller open water characteristics as well as numerically model cavitation. So, and then I'll be covering about the near field noise, which the workshop talks about, and then I'll be talking about the far field noise estimation methods. So coming to the noise sources, this is a vessel wherein the initial noise that we see is the flow noise. This is mostly due to the turbulent flow surrounding the vessel. The turbulent pressure fluctuations act as a noise source. And the secondary noise is the splash noise. Because of the wave breaking, the bubbles are generated, and these bubbles, when they pulsate, generate a noise, and then they implode. This leads to a noise source. These two are generally the high frequency noise sources. And coming to the low frequency noise sources, mainly due to the CMM, that is the critical machinery coming from main engine, the noise transmits. The main sources of noise are the CMM machinery, and then my topic of interest here is the propeller noise. How the propeller noise is critical in the overall sound signature of a vessel. So coming to the broad sound spectrum, here we can see noise spectrum, I can say. So the propeller noise is broadly classified as tonal noise, which is a function of the RPM as well as the number of blades. This is mainly due to the interaction of the propeller blades in the wake field, wherein the periodic flow is coming onto the propeller. And the secondary noise source, which is of importance, is the broadband noise. This is mainly because of the incoming, this is because the interaction of the propeller with the flow. So it would be mostly the tip vortex cavitation, tip vortex noise, and the resulting turbulent noise that we can say. So here we can see this is so this is what we can see. This is a tonal noise. It is a function of blade pass frequency. And this is the radiating broadband noise. So let us take the case of cavitation. In the cavitation also, we will see these two types of noise. One is a tonal and the broadband noise. The broadband noise in cavitation is mostly because of the cavitation bubbles, which try to implode and pulsate, and resulting in a higher frequency noise. So we are going to talk about how we numerically model propeller noise as such. So this is a typical propeller, wherein this is where the tip vortex cavitation happens, wherein the pressure inside the tip vortex, if it drops below the vapor pressure of the liquid, so leads to cavitation at the tip. And this is a boss cavitation because of the low pressure zone at the boss cap hub, boss hub, which would be leading to a loss in pressure, negative pressures behind the hub, which, if they drop below the vapor pressure, would lead to cavitation. The major source of cavitation in a propeller is due to the sheet cavitation, which we can see here. So this is because of the high angle of attack that the propeller leading edge would be facing. And the cloud cavitation, this forms at the collapse of the sheet cavitation. And here, when this bubble cloud implodes, which would create damage to the propeller, and this kind of cavitation leads to loss in thrust. And the final one, which is the root cavitation, which is highlighted at the blade root. This is mainly due to the flow recirculations and formation of negative pressure at the root. So coming to the available numerical methods which are there for us are the higher order method, that is a Rayleigh-Placid model. This is a Rayleigh-Placid model. This is a second order model wherein R double dot or the radius of the bubble with variation in time can be calculated using this formulation. Here in this model, the major considerations are the fluid viscosity, kinematic viscosity, and the surface tension. The major assumption also is the bubble modeling is performed. The bubble modeling is considered as bubble is assumed to be spherical. And coming to the lower order model, which is the Schauner-Sauer model, this is the first order model, wherein the major assumption is the higher order R double dot is neglected, whereas the kinematic viscosity is neglected and the surface tension is neglected to find the radius of the bubble. So here what we consider is, rather than a single bubble, we consider it as a distributed bubble. So this model is widely used in the industry to estimate cavitation, and it is computationally inexpensive when compared to Rayleigh-Placid model. So what we did here was we considered the case of SVA post-stamp test case propeller. The objective of this workshop was to estimate propeller open water characteristic, like thrust coefficient for this propeller, wherein it is inclined at end shaft axis of 12 degrees. And the objective here was to numerically, to experimentally model cavitation in the cavitation tunnel. And the secondary objective here was to estimate the pressure pulses. So the pressure probes are created above the propeller here, wherein the time history of pressure pulses are computed in experiments. So this is just a top view of this workshop wherein the propeller is shown here. So the pressures are measured at probes highlighted here. So this is the inflow velocity, this is the suction side, and this is the pressure side. Here open water simulations are performed. So what we try to do is we try to numerically model the same propeller, wherein the diameter of the propeller is 250 mm. So this is how the propeller looks like. So in the numerical assessment, we used a sliding mesh interface technique, wherein we have exactly replicated the cavitation tunnel. Here we can see the blue color, which is indicating the stationary domain, and the rotation of the propeller is given at this interface. We have used a sliding mesh interface technique for modeling the propeller rotation here. So this is how the propeller would look like. So we have created some mesh refinement zones where our area of interest is to find the pressure pulses here. And we wanted to numerically model the tip vortex formation. So we have created refinements at the tip vortex. So this is a typical sectional view wherein we can see how the tip vortex refinements have been performed. So coming to the results, this is how the animation would look like, the shedding of the tip vortex. So this we have performed using a DES simulation. So this is a test case wherein initial assessments we have performed using a RANS model, wherein the thrust coefficient is compared with experiments With using a RANS model, we have an, the accuracy close to 2%, wherein using a higher order model, that is the detached eddy simulation model, which is a combination of RANs in the near field near to the propeller, whereas in the a zone above, away from the propeller where these eddies are dominant. So these eddies are, rather than modeling, we have tried to resolve these models. This is a higher order model and it is computationally very intensive. So we just tried with this case to see how these DES models are faring with the RANS simulations. So using a DES, we could get a result close to 0.7%, which is under 1%. So in this workshop, there are other participants from Chalmers University and University of Texas Austin and SSPA. So our results were very close. Our results of DES, in fact, were very close with experiments, whereas our results from RANS are next to Chalmers. So this is the case for non-cavitating, wherein thrust coefficient is estimated. So the next, I'll be talking about the cavitating case, how we are getting close to the loss in thrust due to cavitation using the numerical methods. So this is an animation which indicates the sheet cavitation, the highlighted blue zone. So this is how our results are. We tried here 3 different methods. One is using RANS, wherein our deviation was around 25% with experiments. And we tried with DES as well, which was also deviating by around 23%. We tried with a highly complex model of LES, wherein the near wall physics is resolved, whereas even at the far away from the wall, the eddies are numerically resolved. So this took almost 2 weeks' time to just solve for 5 propeller revolutions. Still, we find the results are deviating by around 20%, even after using LES model. So the model that was used for cavitation in this case is a Schorner-Sauer model, which is an lower order model, wherein the bubbles modeling is being assumed as not there. Instead of bubble modeling, we model it as sheet. The bubbles are modeled as sheets. So this is how we can see the sheet cavitation on the propeller blade. So when compared with the results for the other participants of the workshop, our results were close to Chalmers, wherein they are also in a deviation of around 17%. So even what we observed was all the participant results were deviating by around 20%. This is the reason behind is the modeling of cavitation using the Schorner-Sauer model. So we are on the task of using the Rayleigh-Plesset model, which is an highly nonlinear and a complex model, wherein the surface tension effects are also to be considered. This model we are trying, but we are facing issues of convergence while running for the Rayleigh-Plesset model. So the next stage of this workshop was to estimate the near field pressures. So near field sound pressure. So what they have done, we are showing the results of the pressure probe 2, wherein the time history of the pressures are converted to sound pressure levels. This is an experimental plot, how the sound pressure would look like. So the peak pressure was occurring at a frequency of around 100 hertz, of an intensity of 163 dB. So our results of RANS were deviating by around 14%, whereas with DES, our results were close to around under 2%. So now coming to the case of near field pressure fluctuations for case of cavitation. So this is how the experimental results were. And our RANS results were deviating by around 15%. DES and LES, which we tried upon, were close under 1%. So coming to the conclusions with regards to cavitation. So the cavitation phenomena as such, if it is our interest to model, then we can verify using the Schorner-Sauer model, which is a lower order model. Even with RANS, we would be able to find out whether the propeller is cavitating or not. So sheet cavitation can be modeled using the Schorner model. The other types of cavitation like bubble and tip vortex cavitation and face or root cavitation are not modeled using this Schorner model. If our area of interest is to find out what is the loss in thrust precisely, then we have to use the higher order model. So coming to the sound pressure levels, LES and DES models are more appropriate to calculate the fluctuating pressures. If fluctuating pressure is our interest, so then in that case, RANS model would not stand good. So we have to at least use a DES model. So coming to the alternate method, so here whatever methods I have with regards to noise, I have talked about the near field sound pressures. If our area of interest, generally the noise is measured at far field and it is converted back to 1 meter distance. So the available methods for modeling the far field noise are the famous FWH method, the Fox-Williams-Hawkins method, wherein the sound generating source, let us take the case of a propeller. Here, the sound generating source is a surface. So the sound is radiated in two terms, that is loading as well as thickness. In loading, the sound is radiated in terms of a dipole, wherein it is mainly due to the force distribution on the propeller surface. Whereas thickness is a monopole term, the sound would be radiating in terms of a monopole. This is mainly due to the flow disturbances caused because of the rotation of the propeller. So the other term, the quadruple term, which is a volumetric term, wherein in the quadruple term, the sound is generated, the sound sources are inside the quadruple volume. This is mainly applicable for high-speed flows, wherein mostly for jet noise, wherein the Mach number is higher. So coming to the alternate methods, there is another method called boundary element method. So what we do here, the fluctuating pressures that are calculated using CFD are mapped onto a surface model. So here what we did, the fluctuating pressures on propeller as well as hull. These are the two radiating sound surfaces. So we have mapped those pressures and we have tried to radiate this sound, these pressures to far field. So typical example, typical results which we are showing here are, these are the blade pass frequencies. We can clearly see using a BEM model, we can easily calculate the 3 peaks of BPFs and the broadband noise as well. The decay of the noise also we could see here. I have just overlapped a machinery noise in this case, just to amplify like how the propeller noise is critical, even at low frequencies as well as at higher frequencies. So here I have considered machinery noise as well as propeller and hull as a radiating surface. So this is a typical plot of sound radiating to far field. On your right is hull and propeller as a radiating surfaces. On your left, it is only propeller being a sound radiating surface at a frequency of around 25 hertz. I have created an animation to just to visualize how the sound would be radiating to far field. In the case of propeller being a noise source, and in the case being hull being a noise source, we can see an animation, another animation for higher frequencies, say around 50 hertz. So here we can see propeller being a dominant noise source, and here we can see propeller as well as the hull. So some sound is radiating from the hull as well. So just I try to cover on what are the various sound, what you call numerical analysis procedures that are available to us. So that's it from my end.
It is now time for Q&A. Please feel free to ask any question.
I'm Dr. Ebenezer from the Department of Ship Technology. How many million cells did you use in your RANs and in your DES, LES? And what's your Y-wall plus?
Sir, in RANs, for the propeller, open water simulations, our mesh count was somewhere around 3 million, I can say, for RANs. For DES also, we haven't quite changed the mesh as such, because the near field, the near wall modeling has been done using RANs. Only the eddies that are resolved away from the propeller are being modeled to the scale of the grid.
And what's the software that you used?
We have used Star CCM for this, and we have done some simulations in OpenFOAM as well. Okay.
We have time for one more question.
Commander Makar here. This was regarding the non-cavitating propeller. You had shown RANS and DES comparison, and there was a reduction to 0.7% error. In your experience, do you feel that to go for a advanced simulation like DES is worth it when RANS is giving a fairly single-digit error?
Yeah, the main objective of my presentation was to emphasize on this part. Thank you for that question. So, if our interest is only to estimate thrust coefficients or torque coefficients,
Yes.
RANS is good to go. We can see our results were fairly under 2%. Whereas if our interest is to find out sound pressure fluctuations, so for that, at least a DES model should be used.
Understood.
Yeah.
And is there a possibility, the next slide, you had an error of around 17% of 20, of the order
Yes,
of 20.
for cavitating case.
Yes. So is there a possibility of probably tweaking your turbulence model in RANS and bringing this error down, or that was it flattened out?
Yeah, for the case in experiments, what we could see here, one of the major source of cavitation was bubble cavitation as well, and the tip vortex cavitation, which was the major source for reduction in thrust. So that is where our results were deviating. So the answer is we are working on Rayleigh Plesset model, which is an higher order model wherein the bubble modeling is done, as well as the fluid kinematic viscosity is also considered in modeling bubble dynamics. So that is where we will be able to match our results, or we will be coming close to the experiments. So the work is ongoing. It is highly complex and non-linear. So we are facing the what you call convergence issues with that. We are working on that.
Thank you.
We will conclude the Q&A session now. Please feel free to continue discussions with Mr. J. Ram Kumar during the breaks. Thank you, sir, for diving into the complex world of propeller cavitation and noise. Your presentation was a valuable contribution to our understanding of cavitation and noise estimation methods.